Hello,
Hello, ready?
ready.
Okay, you're ready, then I start. How was your day this morning? Do
Okay.
anything?
Yeah,
What do you do?
maths and physics.
Maths and physics, good, oh? Keep yourself fit. Okay, let us start. Let's solve some of the problems first. Review with you what we have done. I hope we have done the homework. Okay, checkpoint. Hey, what am I doing? Okay, so far we have covered this part. So you are supposed to use this formula, right? Optical path. Okay, 23.1. You should be able to draw this one. Right? Just a semicircle. CT, and then 1 second will be C, that's all. Radius will be C. And just draw the other one, that one. Right, I'm just drawing example 2. There are more than that. And you can just draw touching all the arc. No? Right? There are a lot of points on this arc there, or this figure wavefront. So you can draw that and then draw the tiny one and then draw the next wavefront. Okay, then show the ray. That's the ray. Okay. 23.2. Find the optical path in the following media. 50 cm in water, reflective index 1.33. What's the answer?
66.5.
Make sure you give a unit. 0.66.5 cm.
665.
Okay. B?
0.225 meter.
Okay. C?
0.200 meter.
Okay. 20 cm or 0.2 meter. Okay. How about this one? Express the optical path in terms. The figure shows a light wave or wavelength lambda traveling from point X, that's your point X, in air to the air glass interface, that's your air glass interface. The optical length is L. The refractive index of glass is 1.5. Express the optical path L in terms of wavelength. What's the answer?
Length equals to 4.5 lambda.
Just count the number of wavelength. They use a picture, a diagram. And the time taken for light to travel from the point X to the interface equals the time taken for light to travel from interface to point Y in the glass. Find in terms of L, the optical path in the interface to point Y. Okay, what's the answer to this one?
0.67 length.
Oh, I think the first part is probably wrong. Right? They give it as L, so they are more asking optical path in air. Then the next one is N1 L1 must be equal to NL. They want L1 is in here. Okay, 0.67 L, correct. Then after that,
So the first one is what, teacher?
this one I think is supposed to be optical path in air. That's why they give the answer as L. Right?
So
I
no
think
answer.
that's the mistake there. Because if not, the first one and the second one is the same thing. Optical path of from the interface to point Y. Interface to point Y, the same, it will still be same as, unless they are asking now, it should be the same as that in air. Okay, then draw, it should be the same waveform that way. Right? Except shorter wavelength, and that distance should be 0.67 L. Okay.
Okay.
2 point source A and B, which are separated by a distance of 30 cm, emit in phase wave with wavelength 4 cm, state and explain whether the constructive or destructive interference occur at the following point. Point X, which lie perpendicular bisector of A and point A and B. Right? That's your point A and B. That's your X. Equal distance away. That's your point Y. Point Y is 50 cm from A and 40 cm from B. Roughly draw, roughly sketch so that you know what is it. For point X, they are equal. So the path difference, you subtract both of them. AX minus A minus BX equals to 0. So it's constructive interference. And the next one is path difference. Find the path difference, AY. AY minus your BY. We want positive answer. So we always take the largest minus the smallest. So 10, then convert it to number of wavelength. Right? Wavelength 4 cm. So you divide by lambda times lambda. Then this one put 4. So you get 2.5. So 2.5 is destructive interference. Okay. Any comment?
No.
Okay. Two coherent sources S1 and S2, emitting in phase wave of 6 cm. A point X is 72 cm. Just repeat 72 cm from both of them, from S1 and S2. Another point Y is 60 cm from S1 and 51 cm from S2. Discuss whether constructive or destructive interference. Okay, at point X, is it constructive or destructive?
Constructive.
How about at Y? Just subtract it, get 0, so it's constructive. But at Y?
So, Chair,
Y?
hello.
Yeah.
So constructive means it's 0, but then destructive means when it has value, right?
Just subtract, and then see how many wavelength. If it's full wavelength, means constructive. If half a wavelength different, or 1.5 or 2.5, then it's destructive. Yeah, calculate if you haven't done.
60 minus 51.
Yeah, constructive or destructive?
60 minus 51. 9.
9, so
Destructive.
9, I'll decide whether it's constructive or destructive.
Destructive.
Okay, subtract is 9, convert the number of wavelength, 9 divided by 6, 1.5, so it's destructive. If S1 and S2 are antiphase, state and explain the changes at point X and Y. Yep.
S1 and S2 are in antiphase, which equivalent to path difference or lambda square.
What happened at X? At X, what do you see now? Constructive or destructive?
Constructive.
Not be constructive. There's a phase different now. There's a path different. So if there's a phase different of antiphase, 180, then it's half lambda. Right? So destructive at X. How about at Y? You have to consider the antiphase there. Antiphase 180 degrees. 180 degrees is half a wavelength. Yeah. Constructive or destructive at Y? Right? That's previously we get 1.5 lambda. Then because of this phase, the antiphase, you have to add another one there or subtract. So you get
destructive.
Okay? So it's a whole wavelength of lambda. So it's constructive. Any comment? Anything to ask?
Antiphase means what?
Say a bit louder.
Antiphase means what?
180 degrees out of phase.
Which means if 180 degree means, that means what? Like
change to lambda.
No, but then S1x, S2x is what then? For the antiphase.
You have forgotten all your physics. Antiphase is 180 degrees. 180 degrees is half of 360.
Completely opposite.
So it will be half a wavelength. That's all.
Half a. No, then the S1y, S2y is 2.
This one you got an antiphase. So you have to add 0 to plus that amount. Right? In case you forget about your formula. Then we have done much earlier. Under your phase 360 equals to x over lambda. X over lambda. Okay. That's your phase. 180. Antiphase means 180 degrees. So this will be half. So x becomes half of lambda. Okay.
Okay.
That's how
no,
we
but then
convert.
the part difference for S1y to S2y, or is it different then?
You got two antiphase, so then you must add an extra difference there. Instead of 0, you must add that amount. And for x, you still have the same amount, but I must add the antiphase there. That's why you make it 2.
That means the original amount plus the antiphase lah. That's why
original
the
difference.
first one.
Original difference is 0 plus the antiphase.
That's how you get whether destructive or constructive lah. Okay.
If it's the same phase, then you just subtract. Okay.
But this is the combination lah of the antiphase. So yeah.
Yeah, this one you must add antiphase in for both of them.
Okay. That means if they are whole number, then it's constructive. If they still got some decimal number, means it's destructive lah.
If it's half a wavelength or 1.5, then it's destructive. Yeah. Any other comment?
If it's like 2.5, also it's destructive, right?
Yeah. As long as there's a half there.
Okay. can move on.
I think there's one question that we got stuck the other day. Yeah, where is it? I just go over with you briefly. It's very fast. Focus 22.
Oh,
I'll send you the answer anyway.
okay.
Okay, you want that as your Y, as your X. So start with the length formula. Right? You have V, so take 1 over U across. So you got 1 over V. Then take this one across. Common factor FU. So it's U minus F. And take the U across there. Take the U across there. Take the U across there. And then divide by F. This one 1 over FU. F and F cancel is 1. And compare the equation of straight line. Okay. The answer is C. This one.
Sure, your slide never changed yet, sir.
Sorry. How come you never tell me one?
You say answer C, that's what I'm thinking.
Okay.
Oh, go to
Focus
first one,
22,
sir.
number 2.
All right.
Okay. Any
Focus
comment?
22.
Focus 22, number 2.
First question, sir.
We have done already. This is just to, I got stuck there for this question
Oh,
2.
no, go back first one, please.
First one we have done already. Why
No,
don't go
just
before that for what? We have done that already.
okay.
It's just straightforward using formula, that's all.
Okay.
Make sure you write down. I suspect you're not doing your homework, you are comfortable because I'm recording it for you. You're not going to learn anything. You have to help yourself to learn. Right? Go to length formula. Right? You want 1 over V. So take 1 over U across there. Then these two common factor is FU. Then U minus your F. Then take your U across there, you get UV. Then what is left over is U 1 over F. And F cancel is -1. Then compare the equation of straight line. Right? And the answer is C. Okay. Anything
Yeah, okay.
Okay, let's carry on.
New subtopic.
Okay, let's go to subtopic. Yeah.
On that Monday, next Monday.
Yeah. What is it?
No, I would like to ask about SEM 2 can answer questions.
Okay, no problem. You just tell me which topic you want to ask so that I'm prepared.
First and second topic.
Okay, no problem. To slit interference pattern. Right, page 160. Syllabus, explain Young's two slit interference pattern. Derive and use a formula for fringe separation in Young interference pattern. Okay, let's go over that. Right, interference of light. We are interested in light. Requirement for two source interference. Right, I hope you have downloaded your worksheet. Then you can write down your answer. Must be coherent. Right, that's important. The two sources must be coherent. Same frequency. Same speed. It can be frequency or same wavelength, same thing. Same amplitude. Right? If you want complete destruction, if you are not particular about complete destruction, then it's okay. We don't need the same amplitude. Same type of same type and plane of polarization, that means sound and sound, light and light. And then the extra for light, this is the extra one. The two slits must be close together. If not, the fringes will be too small to measure. Okay. So young double slit experiment, we are using narrow slit. That means our aperture size is almost equal to wavelength. And the screen slit distance is very much greater than the slit distance. Right? We introduce all the term in a while. Right? Okay, now any comment? Same type.
So what do you mean by same type and plane of polarization?
Funny, how is it disappearing? Same type, that means sound and sound. Light and light. You cannot have light and sound together, interfere.
Oh. Okay.
Then plane of polarization means that if both of them are vibrating up, both of them must be vibrating up, not one vibrating up and then one vibrating horizontally.
Plane of polarization means they're vibrating lah.
We will come to that when we study polarization. Okay. Maybe let me just supposed to be here. I don't know why it disappeared. Okay, this unpolarized. Unpolarized then means that the wave is vibrating. Can be
your slide, it's jam
sorry.
again.
Always forgotten. Okay. In unpolarized light, like we see around us, there's no fixed plane of polarization. So you can represent it as one electric vector vibrating up and down, one electric vector vibrating horizontally. So we put a polarizer, we remove one component. So it means that the plane of polarization must be the same. It means that if both of them must be vibrating in the same plane. No? You cannot have one vertical and one horizontal, and then they will not interfere at all. Like this one, like unpolarized, it won't interfere at all. That's what it means. Okay. Anyway, we'll go into more detail later on. It's the end of the topic. What am I doing? Okay, can you see the picture now? Interference of light. Okay, let's carry on. That's what it means by plane of polarization. Okay, let's set up double slit experiment. Double slit interference of light. Experiment set up. That's your sodium lamp. Right? Provides yellow light or monochromatic source. That's your single slit. That's your double slit. That's your screen. Okay, let's introduce some of them. The purpose of the single slit is to diffract. Diffract. That means it diverge out lah. Diffract the wave. Same. Double slit, each of them diffract out the wave. Right? The one from S1 is going that way. That's the limit lah. S2 is the limit there. And then they interfere here. You can find the pattern only in this region. That's why we will see as bright and dark fringes. Okay, that's what I mean by overlapping. The wave from S2 and the wave from S1, they overlap or they interfere in this region. Okay, so that's the region of interference. So that distance there from center to center, right? Center of the bright fringe to another center of bright fringe is called your Y or X, doesn't matter, right? X means it is horizontal, Y means it's vertical. So be flexible to know, and then that's your distance from the double slit to the screen or slit screen distance is D, and then here is from one edge there, the bottom here, the left edge to the left edge here is D, or from center to center is D. Right? Either way, your book use A lah, but A can be a bit confusing lah. Right? Because you also use A for the slit for the aperture size. So that's why I use D, which will be using D in diffraction grating. Okay, so the single slit, double slit, and the screen are all parallel to each other. The single slit is at the perpendicular bisector of double slit. So what we observe is bright and dark band evenly spaced. Okay, so Young's double slit experiment demonstrates the wave nature of light. It's used to measure the wavelength of light. Okay, this one is okay. These are just various ways of drawing. Right, this author draw it differently. Same thing. There's a monochromatic light source. And there's your X or Y. There's your distance D. That one is from bottom, from right hand side to right hand side. D. Right? A is the aperture size. Single slit, double slit. Right? A is the aperture. Slit spacing. D is called slit spacing. And capital D is called the slit screen space distance. And then this is called interference fringes, the pattern that we see on the screen. Okay,
Go back again. So aperture size is the distance. What's that? The thickness of it, right? So
aperture size is the hole, the aperture.
Yeah, the size of the hole.
We are not interested in the vertical. Okay, we are
what are we interested
in? The horizontal. Horizontal is the one called diffraction. The vertical one doesn't cause diffraction. That's why the vertical one is still the same. So all
vertical still constant lah.
Vertical one still constant. These are all the image there. That's why we see horizontal. Right? This one, this side is called diffraction only.
Diffraction, okay. Then you'll go through either the X or Y one lah. Okay, we'll go through either one of it. The screen. Hello.
Okay. Yeah.
Yeah. Okay.
This one you have studied in your STPM already.
Yeah.
Right? So you should be able to describe it. Alternate bright and dark, evenly spaced fringes are observed on the screen. Number of fringes, or you can call it bands, obtained depends on the amount of diffraction occurring at the slit. And this in turn depends on the width. Yes, what's the problem?
After this, can just have 5 minutes break for all this.
You should have told me just now if you want a break.
Oh, no, because my earbuds are dying already. That's why I'm asking. It's not to say I don't want to have the class.
I thought I'd take you 1 hour, but anyway, you want a break, we'll give you a break in a while.
Oh. Yeah, no, I know. Okay.
Fringes are found only on the region of overlap. Right, we'll go into that in a while. Right, remember that is your slit. We look at the plane view. That one is a white slit. White slit, there's your diffraction. That's a refraction. From this slit, there's a diffraction. So the interference pattern is found on this area only. So this is called region of interference. And then if this is narrow slit, right? This one will diverge more. So the interference pattern is greater. The region of interference pattern is more. So you see more bright and dark fringes here. Okay, any comment? Right, just to show you, if it's a white fringes, white slit, less diffraction. Narrow slit, more diffraction. So this region of interference is only where the wave from S1 and S2 will meet, that's all. So it's what this region of interference for narrow slit is larger, that's all. Any comment? Anything not clear?
Clear.
Okay, rather than turn it off, I give you 5 minutes break. Make sure you don't take too long.
Yeah, when you give in the new link, then I'll be on already, teacher. Okay,
I won't
you.
close it down. I just carry on. Just wait for you to come.
Okay. Then you can stop the recording, I guess, teacher.
Yeah. Okay, ready to start? Ready to start, ready to start.
Ready.
Okay, let's start then.
So you can hear me, right?
Yeah, can hear you. I said turn on too low, too soft.
Oh, yeah.
Okay, so I just explain to you if it's a white aperture, then this is very region of interference very little only. This one no interference occur. Outside no interference occur. Only occur in this region. Right? If it's narrow slit, then the diffraction is greater. Then region of interference also wider. Okay, so if we look in terms of intensity, that's how we see. Right? Intensity is evenly spaced, and this is the according to the graph, intensity against distance, we should see a dark line. Okay, but we don't see a dark line. We see a dark band. Right? That's the reason. That's the reason. The reason is because we have what I call threshold of human vision. Below certain intensity, we cannot see anymore. Right? Because even though there's still light intensity, there's a little bit of light, we will consider as darkness already. That's what I mean by threshold of human vision. Just somewhere around there. Right? So that's why we see not a dark line, but a dark band. So the weakness in young double slit is we don't know. We are supposed to measure from center to center. Where's your X or your Y? But we are not sure where's the center. Right? We're not sure. We have to approximate. Intensity of the band is the same. That's what it means. Threshold of human vision causes the annulment. Annulment is the cancellation position to appear as dark fringes rather than dark line. Okay, if you use Huygens principle to explain, right? You got plane wave coming, or parallel rays of light will produce plane wave. Then at the slit, it's just become a point source, right? Because the slit is supposed to be the size of the wavelength. And the point source will produce your spherical wave. And the double slit are on the same wavefront. On the same wavefront. That's how we get it coherent. And then the point source from S1 and S2 will produce their own spherical wave. This one is from S1. Sorry, this one is from S1. And then S2 is this one. Right? The broken line is your trough. The dark line, this dark line is your crust. So S is this one. S1 and S2 are point sources. A slit, right? If you use a slit, then it's a line of point sources. Parallel rays fall on the slit S1. Right? That's your parallel rays here. Fall on your slit S1. So the purpose of the single slit diffracted the incident monochromatic waves into circular waves, into circular wavefront. The wave leaving the double slit are from the same wavefront. That's what it means, from the same wavefront, leaving the double slit, right? Known as division of wavefront. That's how we get it to be coherent. That means they are the point source S1 and point source S2 are coherent. Coherent wave leaving the double slits are deflected and interfere in the region of interference where we find the interference pattern. Okay, anything that's not clear? Anything you want to ask?
All okay, Che. Let me read and then I'll come back to you, Che.
Okay, so this one show you if you put a screen there, if you use light, then you see dark, bright, dark, bright. That's all. Right? That's your region of interference, where the two wave from S2, S1 and S2 will meet here. Okay, so that's your worksheet there, 19B and 21A, that's the answer. Right, and then 21B, C and B and C, if you want, you can write down. Did you download? And tell me you didn't download again.
Did.
Then copy down if you have the worksheet. Copy down so that you can
Copy
remember all
already,
this. All these things must be in your head. Memory work. Okay, need more time?
No, all good to go. Good to go.
Okay, I'll go to the next slide then. This is just picture to show you, that's all. You can get it from internet. But problem with internet is you cannot use a white light source like that. You use a source like that, a lamp, then you must have a converging lens there. Make sure it's parallel. Okay, so this one is just trying to express the wave coming out from S1 and S2, where the path difference is 0. That means at the center, perpendicular bisector there, on the screen there will be path difference of 0. Both of them have the same wave. So that is constructive interference. Or the first dark line, lambda over 2, destructive interference. At this point there, where one is going up, going down. Remember, this wave is continuously moving. So it continues moving. Even though it may show you 0 at 0, but after that, it will move. Right? So you will have also this cross and trough to interfere here at the screen here. Okay. So this one also trying to express you the wave coming from here. If it's path different or lambda, then you'll be constructive interference. Path different of 0, constructive interference here. Destructive is half wavelength, half a wavelength here. So here, from S1 to the screen or S2 to the screen, we see displacement distance graph. On the screen itself, the observation is your displacement time graph. That means this wave will continue moving. Right? But you will see this, the pattern doesn't change on the screen. See displacement time graph. Then you must know the first one, m equals to 0, called the central breadband, or path difference is 0. Right? The next one is lambda, path difference lambda, which is here. That's a path difference lambda. Okay, So this one is just trying to, right? You must be able to label. Right? Some maths will want to call a top positive, bottom negative, but physics we don't bother. Right? There's a lambda here, there's a lambda there for bright band, center bright band, path difference is 0, and then okay, so that's your path difference. I use PD or it can be delta. Okay, so the next one will be 2 lambda there. Then for destructive interference, there will always be half. So this one will be half. This half there. This one will also be half. Right? Must be able to label. Right? Same thing. Must be able to label here. This one is just trying to express itself. Path difference is 0. Path difference is lambda. Path difference lambda also. And this half lambda. This half lambda. Okay, there's a lot of work drawing this picture. That's why we calculate path difference easier. Okay, or we can use Eugen's principle to explain, right? The bright and dark fringes. Okay, so I'm trying to relate, right, that wavefront, that diffraction pattern. Trying to explain that. So that's your P. That's your perpendicular bisector, the red line, red broken line. So you should be able to label. That's the center one. This one, center one. Your M equals to 0, M equals to 1, M equals to 2, M equals to 3, M equals to 4. Then 1 here, 2 here, 3. Right? So the path difference for this one is 0. Path difference is lambda, 2 lambda. General equation is M lambda. Okay, M is 0. 0 is here. 1 is here. Right? But dark fringe, you don't have a 0 dark fringe. You start with 1 here, then 2 here, and then 3 here. Or half here, half wavelength, path difference is half wavelength. This one is 1.5. This one is 2.5. That's all. Or the general equation is M minus half. Right? Instead of writing all this one up, series, we can write it as M minus half, bracket, lambda, where your M is 1, 2, 3. Okay. Question: R and S are point sources of light. Point P is on the screen. R and S are in phase. Intensity at P is 0. R and S is 180 degrees out of phase, or we call it anti-phase. So what is the intensity at P now? Yep, what's the answer? Intensity at P?
One.
Bright or dark? 0 or maximum?
Maximum.
Okay, be maximum. We have a phase difference. We have done the calculation already. This one, we are just applying what we have learned. We are not paying attention in class.
Okay.
We just did that a while ago. We just did that a while ago there. Right? If there's an anti-phase here, if they are in phase, that's how we calculate. If they are anti-phase, we have to add an extra there. Instead of 0 there, we have to add an extra there. Right? Same with same. So at Y, we also have to Y, that's your Y. You have to add the antiphase there. Antiphase is 180 degrees out of phase. 180 degrees out of phase is a path difference of 0.5 lambda. Okay or not?
Okay.
You'll be using a lot of this. Make sure you understand it, not you will be lost. right? Minimum or destructive interference occur. Phase difference of 180 degrees is the same as the path difference of half lambda. Okay, that's how you just turn on the light, turn on the power supply. Any question, anything else to ask? If not, let's carry on. Okay, plain view. I think your book gave different value from me. Your book tend to be a bit conservative. Aperture size is usually 0.1. This one, aperture size. You cannot go too small, right? Because we have to sketch to use stylus to scratch on the double slit. And 0.1 is very small already. Right? D from center to center is 0.5. Okay, as I say, your book magnitude is a bit too conservative, too small. Either you can take it from top there to the bottom here, right? Top to top, if you like, top to top, or from center to center is your D. That capital D is about 2 meter or 1.5 meter. You need to know roughly the magnitude. And then we will find X is read on the screen, or Y. That's called your fringe spacing. Okay, so if we calculate using this formula, we will derive for you later. Right? That formula, lambda, if we take it as 400, 10 to the power minus 9, D, capital D is 2, that's 2 meter. Then that small d is 0.5, change it to meter, so we get 1.6. Now you can see that using all these magnitude, we get X is very small, very hard to measure. That's why you have to use vernier, or we call traveling microscope. Okay, question. How many wavelength is this one? This aperture? Okay, and tell me. For wavelength of 600 nanometer, how many wavelength is this aperture? This one. What's your answer? Can?
Where are answer?
Times 2.
It's just 0.1 divided by 600. Lor.
(1.2 times 10 to the power 94). 1.2 millimeter. 1.2 millimeter.
Do you convert it or not? Do you convert it to all millimeter or all to meter? You need to convert it first.
Millimeter. Actually, to meter. Sorry. Yeah.
Your answer is completely wrong. Don't know what you're doing. Right? You just divide by 600. Change to meter. This one change to meter. Then this is 600. I've done something wrong here. Looks like I've done something wrong here. I'm always very careless. 0.1. Okay. Make sure you know how to calculate this. We have done it earlier already. You tend to forget because you don't do homework. This is your division, if you like, on your scale. This is the length. Okay, Ken? Anything not clear? Okay, yeah, okay, we go to the next slide then. Okay, that is your, you can answer your 18 and 19. Right, your worksheet. 18 and 19, write it down. All these things must be in your head. Okay, need more time?
No.
Okay. Show me your worksheet. I want to see your worksheet. Turn on your video. Show me your worksheet.
No, incomplete need to do also.
Did you print out your worksheet or not?
Yeah, I print out, sir, but
Then show it to
incomplete the
me.
thing.
Show it to me. I want to see on the screen there. I want you to be comfortable. You must write down yourself to learn. Force yourself to learn. That's the problem with recording for you. Yeah? Show me your video. Show me on your video there.
Okay.
Why take so long?
Times 5 equals 12.
What is happening? You're supposed to show me on your video. You're not turning on your video on. If you are sick, you should cancel the class.
No, I just coughing a bit. Teacher, I will first that show you the thing the next class, sir. No.
Don't show me the next class. You are not telling me the truth that you didn't print out at all. How are you going to study?
No, I did, teacher, but then not fully completed. So,
If you print out, you should be able to show me on the screen now. Then I can see now whether it is print out or not. So
my webcam not working, sir.
Cannot be. I cannot. If you cannot not working, you cannot have a class at all. It's just that you did not switch on your video.
No, serious, teacher, my one cannot on.
Okay, let's derive this equation. Right? Let's focus on this triangle. Call the path that triangle there, 90 degrees. Right, which is this one. Okay, there's your XM. Remember, XM is the M bright fringe from the center to the M bright fringe. That's called the XM. Okay, that distance from double slit to screen is donkey, D, capital D. Right? That set from center to center of S1 and S2 is called small d. And then S2N is your path difference, delta, right? Which I magnify for you here. That's your delta, that's your D. That angle is theta, this angle is theta, right? I call it theta. Remember, this is very large. This is very small. So we are just using approximation. S1P and NP are the same, equal length. Okay, it doesn't look that way in the picture there, but roughly they are equal length. That's why we show this is the path difference. No, that's the extra length there. That this ray from X2 have to travel, or the wave from S2 have to travel. So for constructive interference at the nth maximum, the path difference delta equals to m lambda. Right? The path difference there is equals to m lambda. Implying that means I want to subject sin theta, take the d across there, divided by d. Okay, so that is your path difference, the extra distance that this way, the way from S2 has to travel compared to S1. Okay, now let's focus on this triangle. Right, same. This is your D. There's your theta. That triangle. So we know XM, we know D as your angle theta. So taking the tangent XM over D. Okay, and remembering the angle is very small. XM is the distance from the center to the end right fringe. That D, distance from source to screen. Right? And the angle theta is very small. And this tangent theta equals to sine theta. Then we have got our equation already. This one equals to that. Any comments so far? Anything that is not clear? Anything to ask? Make sure if you are sick next time, don't have a class.
Okay.
Okay, so that's the equation that we have derived. Okay, there's a capital T across there. That's equation 1. So m plus 1, we just m plus 1 here. Okay, that's second equation. Then we subtract. Right? Remember the distance between the m plus 1 and m is your x. Right? That is your x separation. Sorry, the fringe spacing. Sorry, yeah, the fringe spacing is called the fringe spacing. This one subtract that, you get lambda over d. So that's the equation that we want. Yeah. Okay. Anything not clear?
So far, okay.
Okay. We have considered xm plus 1. X is the distance from one maximum to the other successive maximum. That means from this maximum to that maximum, or from this maximum to that maximum. That's your value of x. Right? That's your example. Right? Just imagine there's a lot of right band. If we call this one xm, then this one will be, the next one will be x minus m. Okay, factors affecting the interference pattern. We are basically using this formula. Explain. And using this formula that we studied earlier, intensity is inversely proportional to distance squared. Okay, so these are all the parameters. X, Y, fringe spacing. D is a screen, right? That screen, and that double slit spacing. Small d is a slit spacing, or your book call it A, right? From center to center of the double slit. Lambda is a wavelength. Okay, so all the explanation is based on this formula. Effect on X. Right? We increase D, then X will increase. But increase D, the brightness will decrease because your intensity depends on distance. As D, that small d, increases, that one increase, this one decreases. As lambda increases, that one increases. The band widens. Blue light has a shorter wavelength. Right? Blue light has shorter wavelength. Right? For blue light, shorter wavelength compared to red light. So the fringes of blue light is narrow compared to red. Okay, so your worksheet number 17, that's the, you are required to know all these terms. You can write down the term there. all this term you must remember it so that when your book use it, then you know what are they, what is the meaning, what do they mean.
它是大概答案是146。
Double slit, single slit, decreasing S, right? The single slit, S. Sorry, S is that distance there. Sorry, I get a bit confusing using the same symbol. That's your distance S. So if you decrease S, you are bringing this source and this single slit nearer to the double slit. So you are bringing the source nearer, so the brightness falling on the double slit is now larger or bigger, but it doesn't affect, right? The distance S is that S there, the distance there is not in the formula, so it doesn't affect your X, it affects the intensity. That's all.
28。
Widening the single slit, right? The single slit there, we widen it, we allow more light to pass through. So we increase the intensity. So we increase the brightness here, initially only. Right? Why is not affected? Because you don't see it here in the formula. Right? Single slit aperture doesn't come into the formula. So it's not affected. If you widen it too much, right? Remember, it will cause the image to be blurred as the source becomes incoherent. Right? Just go back to this picture to help you understand what is happening. Right? Same. This one, right? You will have two, if you widen it too wide, then you have not only point source, you have many point source. So each of them will have their own spherical wave coming out. Okay, same like here. If you widen it too much, then it is normal a point source. It becomes a series of point source. So the point source are no more coherent, right? Because some of it are on different wavefront, on different part of the wavefront. Right? This one will be on the maximum. This one will be slightly below the maximum, and further away will be further and further away from the maximum. Okay or not? Any comment?
Not sure.
Okay.
Yeah.
Let's carry on. Okay, that's what it means by here. Cannot widen too much here, a little bit, okay. So if your point source, you see bright and dark fringes. Bright point source, you see bright point fringes. But if you use slit, then you will see bright fringes. That's all. Point source will give the same fringe system, see? The same X is the same. But the slits, there's line of point source. Slit can be considered line of point source. Give brighter fringes by reinforcing the pattern. Right? You see brighter because this is just a point only. This is just a series of points. Okay, effect of changing parameters. Right? That's your, if you increase your wavelength, you increase Y. Right? Or wavelength is proportional to frequency. Sometimes they want to ask you what happens if the frequency is increased. So you increase the wavelength means you are decreasing the frequency. Fringe spacing of red light is greater than blue light. Right? Can see from the formula. Right? Y for red, longer wavelength, Y is larger. For blue, shorter wavelength, Y is smaller. Okay. So you don't need to know about intensity is proportional to frequency squared. So what does it mean? Let's look at the picture. That's for blue, right? Or violet. Blue or violet band, that's for the red band. Okay, so the red band is wider than the blue band because the wavelength is larger. We call it band widening now. Intensity becomes lower than the blue light. Why? Because it has the intensity has to spread out over a bigger area. Here, this one is smaller area. Okay, so that's why this is to show you. If I stretch the red one to bigger band, then the intensity will go down.
Okay.
Okay, same thing. This is to show you that's M equals 0, M equals to 1, M equals to 2. Right? The dark one is at the center here. Sorry, I should use color, forgotten to use dark. Right? There's your violet, there's your red. Fringe spacing, Y is directly proportional to wavelength. You can see from here. Red band has a longer wavelength than violet light, thus have a wider band than violet light. Okay, I think your book doesn't distinguish it. Violet, shorter wavelength, that one is narrower. This one is wider. That's important to differentiate. Okay, so for violet, the intensity is larger because the area is smaller. This one area is larger, so the intensity smaller. That's the same energy has to spread over a bigger area for the red light, red band. Okay, I think we are just repeating, increasing the, right? You increase this, but you have to remember, increase D, this is your D square. You are decreasing the intensity. Okay, the brightness decreases. Slit spacing, increasing D or A lah. Your book call it A, I call it D lah. Right? You decrease this one. Right? Y will increase. Sorry, increasing D, then your Y will decrease, as this one say. If you increase that one, this one will decrease, but it doesn't affect the brightness. Keeping D constant, or this A constant, but increasing the width of the slit. If you increase the width of the slit, more energy can pass through, so the band will be brighter. But it doesn't affect your Y. Okay, if you use white light, right? White light would be, the central fringe would be white as all colors interfere constructively at the center band. Right? White with color fringes. These are color fringes. Right? The red one will be at the end there. And higher order a bit harder to distinguish, but you see the different color. Right? Different color more. But we are interested in the center, and center one is white. Then you see all the rainbow color on either side. Oh? The red one will be at the extreme end there. For higher order, fringes will be, you see different colors, with blue being deviated least. Remember the blue, shorter wavelength, deviated least. Red, longer wavelength, deviated most. And others in between, other color in between.
No, I never seen it.
Same thing, if we increase our slit S1 and S2, right? Initially, we allow more light to pass through. So it becomes brighter, the band becomes brighter. But we increase to white, remember there? They are, right? It's no more from a point source now, it's from different point source, but the point source are no more coherent. Right? They are incoherent sources, not from the same wavefront, the point source. So it becomes blur and the pattern will disappear. Right? Laser, collimated is narrow beam. You don't need to know that much detail. Narrow beam, it produces coherent and it's one color, monochromatic. That's all you need to know. Danger of laser, that one is high voltage. Do not look, right? It may blind you because your lens will focus the light ray. The beam should not be directed to a reflective surface. A reflective surface, the light can reflect to your eye. So wherever you use it, you always send it to a dark surface or matte surface. Right? That's dull surface. And then in a room that is well lighted, turn the light on, don't turn it off. Okay, so you use laser, then you can replace a single slit with the laser. So if you use a horizontal, just now we use vertical slit, now we use horizontal slit, then the diffraction is in the vertical plane. Right? These are just application, that's all. Laser is a coherent source of light. Each double slit behaves as a narrow slit, causes diffraction. We are just repeating. The wave from the two slits interfere on the screen. Then we see vertical interference pattern. Okay, explain whether we can obtain interference pattern with two lamps. Can or not? Yep. What's your answer? Can or not? Why take so long to answer? Explain whether we can obtain interference pattern with two lamps. Cannot. Right? Light source, example, a lamp is an incoherent source. It's no more a point source. So the wave coming out at different point on the filament are all not related to each other. That's why we call incoherent. Both lamps are incoherent source of light. Okay, that's a 19A worksheet. Explain whether we can obtain interference pattern with the setup. Right? We use a lamp. Can we use this setup or not? Yes or no?
No.
Why not?
You will interrupt the formation of the image.
Say again.
You will interrupt it.
The lamp is not a coherent source. It's not a point source. Right? Even though you get on internet, it shows you spherical wave. That's correct, but the lamp doesn't give this spherical wave. It gives many spherical wave in different order. So cannot. No, light source example lamp is an incoherent source. Right? Internet is free, but you have to be careful when you use it. Thus, light falling directly on double slit would not cause interference. Right? Before we can carry out this experiment, we have to have a single slit to get a point source. Right here, right? Have a single slit. So lamp is an incoherent source. Thus, light falling directly on the double slit would not cause interference. Single slit diffract, you must have a single slit diffract so that light falling on the double slit will be from the same wavefront. That's how we get coherent for the two slit here. In lamp, the waves are arriving at a single slit are incoherent. Right? They come in different, not coherent. They come in different phase. So we use laser, okay. Then we don't need to use a single slit anymore. Okay, so we have completed that. So now I think I will stop here unless you got a question to ask. So you are supposed to do 23.2 and complete your worksheet. up to the part I have taught you?
Not 23.3 Acha checkpoint.
Oh, sorry, 23.3. My carelessness, 23.3. Anything to ask? If not, I will stop here. Anything that's not clear, you want to ask?
No, I want to study for that SEM 2 thing and then ask you lah, Acha, better.
Okay, so let me know which topic you want me to discuss with you on Monday.
Okay. Okay, bye-bye, Acha.
Bye-bye.